Welcome to Fun Facts Online. Today, we journey to the most geologically violent place in our solar system. A world painted in sulfurous yellows, reds, and blacks, perpetually tortured by its giant parent planet. We're talking about Jupiter's moon, Io. Forget quiet, cratered moons. Io is a realm of fire and brimstone, with hundreds of volcanoes erupting at once, creating a fiery symphony that shapes its surface, its atmosphere, and even the space around Jupiter itself. So what is the engine driving this incredible chaos? The answer isn't deep inside Io, but far outside it. Io is locked in a gravitational tug-of-war. On one side, you have the colossal mass of Jupiter. On the other, the rhythmic pulls of its neighboring moons, Europa and Ganymede. They are in what astronomers call an orbital resonance. For every 4 times Io circles Jupiter, Europa circles twice, and Ganymede circles once. This regular alignment acts like a recurring push on a swing, preventing Io's orbit from ever becoming perfectly circular. As Io is forced along its slightly elliptical path, Jupiter's gravity kneads it like dough. The moon's surface bulges and flexes by as much as 100 meters, or 330 feet. Imagine a tidal bulge on Earth, but instead of water, it's solid rock rising and falling by the height of a 30-story building. This constant flexing generates immense friction and heat inside Io's mantle, keeping it volcanically hyperactive. For decades, scientists believed this heat created a global, subsurface ocean of magma, a continuous layer of molten rock fueling all the volcanoes. It was a neat and tidy explanation, but recent data from NASA's Juno spacecraft has challenged this idea. By measuring tiny wobbles in Io's gravitational field as it flexed, scientists found that Io's interior is more rigid than a global magma ocean would allow. The current leading model is more complex and, frankly, more interesting. Instead of a molten sea, Io's mantle is likely a magma slushy. Think of a mostly solid, porous rock matrix, but with interconnected pockets and channels filled with molten rock. This slushy can still generate the mind-boggling amount of volcanism we see as magma works its way up through fractures in the crust. So we have this incredible internal engine, but what does it actually create on the surface? Io's volcanic features are unlike anything on Earth. The most common landform is the patera. These are vast, steep-walled volcanic depressions, similar to Earth's calderas, but on a much grander scale. The average patera on Io is 41 kilometers wide. The largest, a behemoth named Loki Patera, spans over 200 kilometers, or 124 miles, across. You could fit several large cities inside it. Many of these patera are filled with active lava lakes. These lakes of molten silicate rock are covered by a thin, dark crust. Periodically, this crust breaks apart and sinks, exposing the incandescent magma beneath. This causes a dramatic surge in heat that we can see with infrared telescopes. Some lakes, like the one at the volcano Pele, seem to be constantly overturning, making them persistently bright. Others, like the giant Loki Patera, have episodic events, where a wave of crustal foundering sweeps across the lake. In a surprising twist, the Juno mission found that when this lava solidifies, it can be as smooth and reflective as obsidian glass. Spreading out from these volcanic centers are extensive lava flows. These are primarily basaltic lavas, which are very fluid. Thanks to high eruption rates and Io's low gravity, these rivers of fire can travel for hundreds of kilometers, constantly repaving the moon's surface. The landscape is so young that we see almost no impact craters. They're all buried under fresh lava. Perhaps the most visually spectacular result of all this activity are the plumes. These are colossal fountains of gas and dust that erupt hundreds of kilometers into space. There are 2 main types. First are the Prometheus-type plumes. These are the most common, reaching heights of around 100 kilometers. They happen when hot lava flows over surface deposits of sulfur dioxide frost, instantly vaporizing it into a jet of gas and dust. Then you have the Pele-type plumes. These are the giants, the showstoppers. They can soar up to 500 kilometers, or over 300 miles above the surface. These are powered by sulfur dioxide and sulfur gas exploding out of the magma itself at a volcanic vent, carrying fine particles of silicate rock with them. These plumes are responsible for creating the vast, colorful rings of material we see deposited around many of Io's volcanoes. And just when we thought we had a handle on Io's volcanism, new research has revealed something else: stealth volcanism. Using the James Webb Space Telescope, astronomers detected emissions of sulfur monoxide gas from regions with no visible hotspots or plumes. The theory is that these are eruptions of pure, superheated gas. Because they contain no dust to reflect sunlight, they are essentially invisible. These stealth plumes could be a huge, previously unknown contributor to Io's atmosphere. Amidst this volcanic chaos, Io holds a paradox. It has mountains, and they are enormous, some dwarfing Mount Everest. But unlike on Earth, these are not volcanoes. They are tectonic mountains. The process is incredible. As new lava constantly buries the surface, the crust below is pushed down and compressed. This immense pressure causes huge blocks of the lithosphere, tens of kilometers across, to fracture and get thrust upwards, creating massive, isolated mountain ranges. All this volcanic activity, from lava lakes to stealth plumes, is the source of Io's atmosphere. But calling it an atmosphere is generous. It's 1 billion times less dense than Earth's and is made almost entirely of sulfur dioxide. And this tenuous atmosphere lives a bizarre and violent life. On the sunlit side of Io, the relatively warm surface causes frozen sulfur dioxide frost to sublimate, turning directly into gas and feeding the atmosphere. But Io's orbit takes it into Jupiter's shadow for about 2 hours every 1.77 Earth days. During this eclipse, without sunlight, the surface temperature plummets. The sulfur dioxide gas in the atmosphere instantly condenses and freezes, raining back down onto the surface as snow. The atmosphere effectively collapses, with its pressure dropping by as much as 80%. Then, as Io emerges back into the sunlight, the frost sublimates again, and the atmosphere rapidly rebuilds itself. This cycle of total collapse and rebirth happens every single Ionian day. While sublimation drives the dayside atmosphere, direct volcanic outgassing is also a huge contributor, providing 30 to 50% of the total gas, and it's the primary source for maintaining an atmosphere on the cold night side and at the poles. But Io's story doesn't end there. Its existence is utterly dominated by its parent planet. Io orbits deep within Jupiter's immense magnetosphere, a bubble of space controlled by the planet's powerful magnetic field. As Jupiter rotates, this magnetic field sweeps past Io at tremendous speed, acting like a cosmic sandblaster. It strips away about a ton, or 1,000 kilograms, of material from Io's fragile atmosphere every single second. This stripped material, mostly sulfur and oxygen atoms, forms a vast banana-shaped cloud that orbits along with Io. But these neutral particles are then bombarded by solar radiation and other charged particles, which knocks off their electrons and gives them an electrical charge. They become ionized. Once ionized, these particles are instantly grabbed by Jupiter's magnetic field and are whipped up to co-rotate with the planet, which spins much faster than Io orbits. This process creates a giant, donut-shaped ring of intensely radioactive plasma called the Io plasma torus. This torus, composed of ionized sulfur and oxygen, glows faintly and gets heated to millions of degrees. It's a feedback loop. The hot plasma in the torus bombards Io's upper atmosphere, knocking even more material loose, which then feeds the torus. The Io plasma torus is the primary source of plasma for Jupiter's entire magnetosphere, making it far larger and more dynamic than it would be otherwise, and it creates a direct visible link between the Moon and the planet. Particles from the torus are funneled along Jupiter's magnetic field lines. slamming into the planet's upper atmosphere near its poles. This creates glowing auroral spots on Jupiter, known as the Io footprint, a shimmering testament to the electrical connection between the giant planet and its fiery moon. Our understanding of this incredible world has been a journey of discovery. The Pioneer spacecraft in the 70s gave us the first hints of its strange nature. But it was in 1979 that Voyager 1 revolutionized everything. Imaging scientist Linda Morabito spotted a giant plume erupting from the limb of the moon, discovering the first active volcanism beyond Earth. The Galileo mission, which orbited Jupiter for 8 years, gave us an unprecedentedly detailed look, mapping the surface, confirming the composition of the lavas, and watching the landscape change between its flybys. More recently, flybys from the New Horizons probe and ongoing observations from the Juno mission and the James Webb Space Telescope are rewriting the textbooks. Juno's gravity data forced us to rethink the magma ocean hypothesis, while Webb has given us our first look at stealth volcanism. Io is more than just a volcanic moon. It's a unique natural laboratory. It allows us to study extreme volcanism that might resemble the early, more active Earth. The tidal heating that drives it is a key process we see in moons and exoplanets across the galaxy. And the intricate dance between its volcanoes, its collapsing atmosphere, and Jupiter's powerful magnetosphere is an unparalleled place to study cosmic-scale physics. As we continue to watch with our most powerful instruments, the fiery symphony of Io will surely continue to reveal its secrets, a captivating and violent masterpiece in our solar system.